now we would like to see the transformer till now. Had losses to contend with. That is due to the hysteresis and the eddy currents. This we are calling it as the core losses. Now, from this aspect, let us see an ideal transformer. An ideal transformer means what characteristics? Firstly, let us take the BH loop. So, we have this BH loop plotted onto orthogonal axis, the vertical axis being the B, the horizontal axis being the H. This is N I by L, Lm. Ni is the MMF, the motive force, and the flux, this is flux per unit area. So, we know that, and we have seen before that this results in a curve which goes, and the area covered within the BH loop in a cycle is the energy that goes off as hysteresis loss, because that is unrecoverable. So, which implies that if this loop is narrower and narrower, that is, we tend towards the loop which is like that, let it tend towards this becoming narrower and narrower, and in the limit let it become just a line like this, which means the area within this loop is almost 0, or in the ideal case the area within the loop is 0. Then there is no hysteresis loss. Hysteresis loss becomes 0. Here hysteresis loss is equal to 0. And then we also need to look at the slope of this. This slope it means that if I want, this slope tells you how much amount of motive force Ni by Lm, how much amount of current I have to pass on the primary of the coil to obtain a flux phi 1 by A for a given core. Now, if this slope is made steeper, then it implies that to get the same flux phi 1, I need to pass lesser current. If this were I1, this will be Ni2 by Lm, and so on. If the slope keeps on becoming higher and higher, which means the permeability is improving, because this slope is nothing but mu. The permeability is going towards infinity. So, in the limit, this will tend to this being almost vertical like that. So, which means this has a mu which is tending towards infinity, this being the BH curve. This is the B and this is the H. So, what it implies, to obtain a flux phi m or phi 1, the current needed is negligibly small or infinitesimally small, or in the ideal case 0. So, that is another point of ideality, where mu tends to infinity. Now, there is another point of ideality that one could note, the same BH curve. You have the H and you have the B. We saw that, let us say, this is the BH curve. After a certain level of B, it saturates, B sat. It loses its magnetism, loses magnetization properties, beyond which it does not act like a magnetic material. Now, if this B sat starts tending to infinity, if B sat tends to infinity, then you will end up with a magnetization curve which is the vertical axis itself. So, a magnetization with which is the vertical axis implies B sat is infinity, mu tends to infinity, permeability tends to infinity, hysteresis loss tends to 0. All these are important features of an ideal transformer. Note that all these would be features of ideal transformer, something that we expect it to have. One more feature that is expected of the ideal transformer is that there should not be eddy current losses. Losses should also tend to 0, which means the resistivity of the core material, because if there is a flux flowing in the core material, there is going to be currents around the flow of the flux in an orthogonal plane. So, if the resistivity of the orthogonal plane is increased, then that eddy current is going to be reduced. Now, if that resistivity becomes infinite, then the eddy currents will also tend to 0. So, the resistivity of the core material should tend to infinity. This implies the eddy currents tend to 0, which means eddy current losses due to I eddy square R core will tend to 0. So, in an ideal transformer, the resistivity of the core material should also tend to infinity. So, for an ideal transformer, the following features exist for them. One is the permeability mu tends to infinity, which makes the BH curve's slope at 90 degrees, that is along the vertical axis. Second, B sat, the saturation flux density tends to infinity, meaning the core never saturates, whatever may be the current that you apply or whatever may be the motive force. Then third, there is no hysteresis loop. The area of the hysteresis loop is 0, which implies hysteresis loss tends to 0. Then fourth, resistivity of the core material should tend towards infinity. This implies eddy current losses are 0. Further, there is a fifth one, which is on the coil. The coil which is wound on the core should have 0 resistance. So, the coils, the winding resistance should tend to 0, meaning the copper, that is normally copper is wound on the core, but copper has a finite resistance. So, therefore, if there is a winding of finite number of turns, the resistance is also finite, and therefore, there is going to be I square or loss. So, the coil's winding resistance, if it is tending to 0, there is no copper loss. The copper loss is I square into R winding will also tend to 0. This would be an ideal transformer with absolutely no loss. So, whatever energy is given to the primary, the same energy goes out through the secondary port. In other words, if there is no load on the secondary, if there is a voltage applied on the primary, there is no current flowing through the primary winding, 0 current is sufficient to set up flux in the primary and flux in the core, and the flux that is set up in the core, which is the motive force set up in the core, will induce an EMF on the secondary according to the turns ratio, and a secondary voltage is developed, with 0 energy being lost in the hysteresis or the eddy current or the copper loss. That would be the feature of an ideal transformer. Now, the practical transformer, because we can't expect to obtain or get or make an ideal transformer, the practical transformer will have a finite mu. Mu, or the permeability, is finite. It is not infinity. The BSAT, the saturation flux density, is not infinity, but a very finite value, and as I said, CRGO has around 1.2 Tesla, CRNGO, cold rolled non-grain oriented silicon steel, has around 1 Tesla, ferrites around 0.3 Tesla, so on. So, it is a finite value, which means beyond this value the core will saturate and will not behave as a magnetic material. The laws of electromagnetism will not hold good. Then the third point, there is a hysteresis loop. Hysteresis loop is not 0 or non-existent, there is a finite area, which means there is a finite hysteresis loss. And the fourth, the resistivity of the core material is not infinite but is finite, which means there is some finite eddy current loss. And fifth, the coil that are wound on the core is normally copper or aluminum, which have some finite resistance, and therefore the coil or winding resistance is non-zero, which means there is going to be a finite copper loss. So a practical transformer has all these to varying degrees depending upon the type of the material used and depending upon the type of the windings used and the way it is designed. Now, how do we represent a practical transformer electrically? Because an ideal transformer we know has a symbol like that. With a turns ratio. This is an ideal transformer. Ideal transformer. What would be the equivalent circuit for a practical transformer? That will be the focus of the discussion in the forthcoming dialogue. Now, let us start with the ideal transformer, and one by one let us introduce the non-ideality and how does it reflect electrically on the equivalent circuit. We shall discuss and see the effect of that particular non-ideality on the equivalent circuit. So, first let us introduce the effect of core losses. Effect of core losses. Now, the transformer, an ideal transformer, is shown in this manner. There is a core and then the secondary winding. Now, there is a source on the primary side, an AC source, and that is called EG. Now, this source is connected to the ideal transformer. So, under normal ideal conditions, when the output on the secondary side is open, there is no load connected, this current I2 is equal to 0, I2 will be equal to 0, and therefore I1 will be equal to 0, which means even 0 current is sufficient to provide, or infinitesimally small current, negligibly small current is sufficient to provide the required ampereturns or the magnetomotive force to set up a flux in the core which gets linked to the secondary to produce E2. This is the primary induced voltage. But in a practical transformer, we said that there is core losses, one of the non-idealities we are introducing. Now, if there is core losses, even when there is no load connected across the secondary terminals, the hysteresis loop is going to be traversed. Every cycle the hysteresis loop is going to be traversed, and for every traversal of the hysteresis loop, the area covered by the hysteresis loop, that amount of energy is going to be unrecoverable. So that energy gets lost, which means that much amount of energy has to be supplied by the source, which means the source current will have some current I naught even under no load conditions, whatever that is. Now that current is not going through the ideal transformer, so it has to go through some lossy element. So we put in a lossy element here, and let us call that one as RC, the core loss component. And the current that is going to flow through this is the whole I naught itself, which flows through this and provides the I square or I naught square RC as the core loss, equivalent core loss component. Now additionally, let us also introduce the finite permeance non-ideality or finite permeability non-ideality, which means mu is finite. So what does it imply? If mu is finite, then the slope is not 90 degree, the slope is not infinite, which means the BH curve is not along the vertical axis, it is going to be slightly away from the vertical axis, as denoted by the permeability, which means that there is some amount of current needed to set up the required flux. There is some amount of current needed to set up the required, there is some amount of current I needed to set up the required flux phi. If this is phi and this is I, phi and the B is nothing but phi by A, and H is nothing but Ni by L. So we could also have a phi I curve, which means a current, finite current is needed to set up the flux, which means that current is also to be drawn from the source even under no load condition. That current is also to be drawn and diverted to the flux producing device or a flux producing component of the equivalent circuit. And I1 should still continue to be 0 because this ideal transformer is not going to take any current to set up the flux. So which means from here I am going to have one more component, and let us call that one as XM. So this I naught which is drawn from the supply is going to split into two components. One is IM and the other is IC. IC is that component of I naught which produces the core losses. IM is that component of I naught which produces the magnetic flux in the core, such that it can be linked to the secondary and have an induction on the secondary side. So these two non-idealities result in such an equivalent circuit. How do we measure this? So, you see that IC is producing a loss in RC, IC square RC. So, the voltage across RC and E1 will be in phase, which means IC will be in phase with E1. E1 is same as EG. IM is the flux producing component which will lag, which is passing through an inductor, inductive reactance, and therefore, I will lag 90 degrees whatever the voltage across the device. So, if we look at the phasor diagram, it should look like this. So, let us first take this to the next page. We go to the next page, we paste. So, if we have, let us say, the spatial coordinates, and along this axis I have EG, which is same as E1, and along that is IC, and 90 degrees lagging will be IM, which in fact produces phi m, the flux, and the resultant of IC and IM will be I naught by Kirchhoff's current law. So, this is I naught. So, this is how it would look like. Now, I naught into E1, I naught into E1 is the VA that is drawn from the source. So, VA drawn from the source will be I naught into E1. IC into E1 is the active power, that is the loss component, which is drawn from the source, and IM into E1 is the reactive power that is drawn from the source for setting up the magnetic flux in the core. So, this will be, let us say, a reactive power Q. This will be the active power P, which is drawn from the source, and this is going to be root of P square plus Q square, let us say. So, RM and XM can be found out from this and this. So, P, the power, the active power, is nothing but E1 square by, sorry, this is RC, this is RC, is nothing but E1 square by RC, and Q, reactive power, is nothing but E1 square across the same inductance divided by XM. So therefore, you have RC which is equal to E1 square by P, and you have XM which is equal to E1 square by Q. So measuring the active and the reactive power, that is measuring I naught and EG voltage, capturing it on the scope, on an oscilloscope, and then computing the P and the Q, that is the active power component, which is watts, the reactive power components, which is VAR, and this of course is VA. One can compute RC, which is the core loss component, and XM, which is the magnetizing impedance or the magnetizing reactance component of the transformer under no load conditions, meaning when the secondary side is open circuited, there is no load connected across the two secondary terminals. So let us do a small example for this particular case of non-ideality, which is we have introduced a finite permeability, and we have also introduced the core loss components into the ideal transformer. So the equivalent circuit is now composed of an ideal transformer plus some added components in parallel. One is the loss component RC and another is the magnetizing component XM, which is basically an inductance LM. So let us say we have a transformer, and at no load it draws current I naught, which is equal to 5 amps. The primary is connected to, that is EG is 230 volts 50 hertz. And from the wattmeter test, that is by connecting wattmeters, the active power, that is power loss, the iron loss or the core loss, the power loss component in the core is 200 watts, let us say. Now, if this information is given, let us find out what is the apparent power. Apparent power, that is the VA. Now, VA we said in the previous, this is nothing but I naught into E1 is I naught into E1, which is 5 into 230 volts. This is the VA. Now, we know that the P in this is the active power here, which is 200 watts given. Then what is Q? Q is root of VA square minus P square, which will be root of 5 into 230 square minus 200 square. So we have the Q. Once you have the Q and the P, RC is given by E1 square by P, which is 230 square divided by 200 ohms. Xm, the magnetizing impedance or magnetizing reactance, is given by E1 square by Q, which is equal to 230 square divided by root of 5 into 230 square minus 200 square, that many ohms. So, this gives RC and Xm, and this can now be used to find what is IC. Now, IC is equal to E1 by RC, which is equal to 230 divided by 230 square into 200, which is equal to 200 by 230 amps, and Im is equal to E1 by Xm, which is 230 divided by 230 square root of 5 into 230 square minus 200 square amps. So, this will give you the core loss component of the current and the magnetizing component of the current, and one can plot the phasor diagram and obtain and see that, let me write, and see that if we have 230 volts, this is E1 or Eg, we are going to have IC, and there is going to be Im, and the resultant, that is going to be 5 amps. So, this is going to be less than, if we look at this equation, this is approximately less than an amp, around 0.8 or 0.9 amps. So, this is approximately 1 amp, and this will be slightly greater than 4 amps, so that you get resultant 5 amps. So, if you calculate this portion, this should be around 4 amps and this should be around 1 amp, greater than 4 amps. So, this would be the vector diagram, and this will be the angle, this is I naught, by which the current lags the applied voltage E1 or Eg. So, what we have done here is introduced two non-idealities, the loss component and the finite permeability component. Now, we also have to see that whatever ampere turns that the primary current is generating, which is N1 into I1, is going to have a motive force within the core of the transformer. Now, that is going to link to the secondary turns N2 and generating a voltage E2, and if there is a load on the secondary, there is a current I2 flowing in the secondary. Now, that secondary current is going to also produce a motive force within the core of the transformer, which is N2 I2. Now, N1 I1 and N2 I2 will be opposing in nature, because on one side the power is entering the transformer, the other side the power is leaving the transformer, and because of this opposing nature, they cancel each other and there is an effective flux in the core. Now, all the ampere turns or all the flux that is produced by the primary does not link all the windings on the secondary, and all the ampere turns or motive force generated by the secondary current I2, which is N2 I2, is not going to link with the primary. So, there is going to be some flux which will not link with the other winding, and that is called the leakage flux. So, there is only a portion of the flux that actually links between the two coils, and that is called the mutual flux. So, we have the leakage flux and the mutual flux, which results in actually lesser voltage being developed across the other windings in the core. Now, all practical transformers will have some flux which does not link the other coils which are in the core path, and they are called the leakage fluxes. And we will see how we try to incorporate the leakage flux component into the equivalent circuit model to have a much more complete picture of the transformer. Further, we need to also include the copper loss component into the model. This we will see